The SD is closely related to the bell-shaped curve. It has a very strong connection with the bell-shaped curve, and that is the primary reason the SD is studied and used as a measure of spread much more than any other. To see how that comes about, first notice that if you have a histogram, you might be able to spot roughly where the average is, but it's pretty hard to estimate how big the SD is just by looking. The root mean square of deviations from average, not so easy, right? Even if you say most of the data are within average plus or minus a few SDs, well, what's a few? Is it 4? Is it 5? Not so easy to figure out. With bell-shaped curves, however, you can see the average. That's the center of the curve as the point of symmetry, and you can also see the SD. How? If a histogram is bell-shaped, then of course the average is at the center. There's unambiguous what the center is. And the SD is the distance between the average and the points of inflection on either side of the curve. There's the average in the center, and to get at the SD, you go on either side up to what is known as the point of inflection, and we will see that on a histogram. First, let's go back to our histogram of ages of our 1174 women. The mean was about 27 years and the SD was about 6 years. If I look at this histogram, it's kind of reasonable. The average should be around 27. You can see that this histogram will balance somewhere in the 25 to 30 range. But it's not so easy to tell that the SD should be about 6 just by looking at that picture. We did a calculation and measured all the ages in standard units, and there, by spotting where the 1 is, you can see that this distance is about an SD. But you really can't tell that so easily from this picture at all. If instead we had looked at the heights of the women instead of their ages, it's going to be a lot easier to study this histogram if we have some edge colors. Edge color equals white is my favorite option that I keep using. That's roughly bell-shaped. Of course, it's not exactly bell-shaped, but it's roughly bell-shaped. Now, if you had to guess an average, what would you guess? Somewhere here? About 64, 65, something like that. Somewhere here. Now, the bell-shaped curve has this way of sort of going down, and at some point it changes to going up. We say it starts out by looking at like an upturned cup, and then here you go and it's a cup the right way up. The place where it changes is called a point of inflection. That's a mathematical quantity, but we will just eyeball it. So here we go, it's kind of coming down, and well, maybe about here is a point of inflection. What's that? 66.5 roughly. That's 65. That's 75. About 66.5. Maybe. So we had guessed the average to be about 64, and we're saying that the point of inflection is at about 66.5, so the distance between the center and the point of inflection is about 2.5. That's what we're saying. We're guessing average equals roughly 64 and SD equals roughly 2.5. We've got the data. Should we check? So we've extracted the heights as a column, and we're going to compute the average of the heights and the standard deviation of the heights. And we get roughly 64 and roughly 2.5. Look at the picture again, and see that you agree that the center is around 64. You might have guessed 64.5, that's fine. So this is 65 right here. 64 is not a bad guess for the center. And the point of inflection, you go down, 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 and now suddenly you're going up, and this right here is around 66.5. And that's how we made our decision, that the point of inflection was 2.5 above the average of 64. And that's why we guessed the SD to be about 2.5. Being able to see the SD this way, the normal curve is one of the very few distributions where you can do it. You sometimes can see it on very basic distributions that have only 2 values. It's a lot harder to see for any other distribution, but you can see it on a normal. And I've been using the term normal equivalently as bell-shaped. We'll make all of this, we'll explain the terminology in a minute. Just to make sure that we can do this again, let's look at the weights of the women. Which also come out to be reasonably symmetric. And if you'll excuse me, I'm going to do my usual thing of getting some edges on this histogram. So that's a normalish distribution, and the center, if I had to guess the average, I would guess 120. It's 120 pounds. That's, excuse me, these are birth weights. That's 120 ounces. Excuse me. SD. Well, down, 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 and then up again somewhere about here is a point of inflection, maybe. It's very rough. The histogram's rather crude. I'm just trying to get some sense. I think the point of inflection might be somewhere here. Centers at 120. This here is 140. The point of inflection, I think, is a little to the left of 140. So I would expect the SD to be not quite the distance between 120 and 140, not quite 20. Something less than that. And I really can't tell how much less than that. But if I had to take my best guess based on this picture, I would guess that the average is 120 and the SD is somewhat under 20. And we can check all this by simply extracting the birth weights as a column and calculating their average and SD. And we get an average of 119.5, close enough to 120, and an SD of not quite 20, somewhat less. So based on the histogram and with the sizes of the bins, we couldn't see the SD exactly, but we had some sense. The standard deviation and the normal curve have a much closer connection as well, and we'll come to that after we have first defined the normal curve precisely.